Okay, good morning, everyone. This is June, and today we will continue on Lecture 6 of RT525, the Advanced Engineering Materials. So, as I have briefly mentioned at the end of the Tuesday lecture, we are going to learn about conduction, right? So far, this class has, as I have mentioned, we are focusing on fundamentals, right? To do this, we learn about atomic structure, right? Bondings, force between bondings, energy between bondings, crystal structure, right? Planes, right? Grain boundaries, crystalline, amorphous, right? And then, using these concepts, we have learned about how mechanical properties can be determined from the atomic scale view, right? So we learn about Young's modulus, shear modulus, right? And then we learn how this is related to the interatomic bonding force and also the interatomic distance, right? And we also learn if the material is denser, then there's very high probability that this Young's modulus will be high again, right? So beginning today, hopefully, I will cover the conduction. All right. So for many of you, when we talk about conduction, you guys will probably think about electrical conduction. Right? But in reality, there is also another very important conduction, and that is thermal conduction, right? And we know that in case of electrical conduction, the carriers are electrons, and for thermal conduction, it can be either electrons or phonons, right? So today we will learn about this key concept, right? So I just wanted to give you a good preview of today's lecture, okay? So yeah, so let's go back to the lecture note. So here is the lecture note. And here we'll jump into the electrical conduction in solids. So we know that some of the solids can conduct electricity, and those we generally call them conductors, right? And it basically has overlapping band gap, right? Right. So if you go back and look, this definition of electrical conduction is the movement of electrically charged particles through a conductor or semiconductor, which constitutes an electric current. Oh, excuse me. Right, so this is the movement of electrically charged particles through a conductor or semiconductor, which constitutes an electric current. The charge transport may result as a response to electric field or by diffusion. Okay? So this field, right? So there's this electric field. And in this case, electrons interact with these electric field. They interact. All right. And this is the charge transport or the current generation due to the electric field or just by the diffusion, right? So if you think about electrons as a particle, right? Every atom's molecules or particles diffuse, right? If we drop ink on a water, the ink atom, the colored atom or colored molecule will diffuse into the water, right? And it'll change the overall color of the water, right? Or if you bake a cookie in a room, and if you open the cookie jar, the smell molecules will diffuse into the room, and you will hear that you will smell the cookie smell in the entire room. So it's the same thing, right? So there is also the diffusion. So this is somewhat induced by the electric field, and diffusion is happening due to in a more natural way, right? Then the current density, the amount of current in a given space, or the current density, can be expressed as a function of conductivity times the magnitude of electric field plus single charge times the diffusion coefficient and the carrier density over space, right? So this is the definition of current density, and we'll go into this term one by one and understand how this is induced, okay? How this expression is have been derived. So above equation is delivered from Drude theory of metals. So this person Drude here. All right, looking pretty sharp. Which theory of electrical and thermal conduction and a metal application of the kinetic theory of gases to a metal. So he applied the kinetic theory of gases to a metal, right? So there was this thermodynamic model to predict the movement of gas molecules depending on this environment, and he applied this knowledge into the electrons. So he considered, instead of gas molecules, he considered the electrons and them as an individual particle. Okay, so this is the Drude model, right? So if you recall your very high level physics, you probably have learned about this Drude model. So as I have mentioned, right? So this current density, right? Basically, if you want to find out about the density over this plane, right? Let's consider this is J. Oh yeah, it's right here, right? This arrow, and here is J, right? And this is your cross-sectional area of your model. Oh, Jesus. Okay, all right. I'm sorry about that. If you look at here, the definition of the current density is change in amount of electric charge over area, cross-sectional area over unit time. All right, so you are basically trying to find how much charge has passed through the given area over a given time, and that is defined as the current density. Okay? All right. So if there is this x and this, and let's say that is your current density. So if you think about it here, the one very thing that I want to point out here is that we already have the direction of electric field, right? And you see all these individual electrons are pointing in opposite direction to this electric field. And this is, if you recall the physics, if there is this electric field in x direction, this electron will move in opposite direction, and due to the which force? All right, I believe everyone remembers this thing, Coulombic force. All right, and this amount is electron charge times electron field. Okay? So there are this many numbers of electrons, right? 1, 2, 3, 4, 5, 6, blah blah blah, right? So if you want to find out about the average velocity of an electron, then we need that information to find out how many charges goes through this given area in a given time. We need to find out about this velocity of these electrons, and that average velocity is called drift velocity. Okay, and this is 1 over n bracket 3x1 plus 3x2 plus dot 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 plus 3x3 bracket. So if you take the x component velocity of all individual electrons and add them all up, do addition, and if you divide by the total number of electrons, then you can get the drift velocity, or the equivalent average velocity of electron in x direction. Okay. So now here I want to give you a new definition. If n is equal to n divided by volume of the system that you're considering, then here you can get number of electrons per unit volume. Okay? Okay? All right. Cool. So if you think about it, the distance traveled in x direction will equal drift velocity in x times change in time, right? Velocity times time. 속력, 속도 곱하기 시간은 움직인 총 거리죠, right? Velocity times time equals the total traveled distance. And you can also express this as change in charge equals one electron charge times number times A times delta X. All right. So here, this is the number of electrons per unit volume, and area times travel distance. This will be the traveled, volume, right? Or you can also define these terms as number of electrons crossing this cross-sectional A at this amount of time. Okay? Okay. All right. So here what you can find is that if you plug in this expression to the original this equation, then you get this current density in x direction will become, by definition, over A times delta T. However, you can express this as now electron charge of single electron times number of electrons per unit volume times cross-sectional area times drift velocity in x dx and change in time over area times delta T. And finally, you get charge of single electron times number of electron per unit volume times drift velocity. Right? And also, if you get a little fancier, then you can get, you say, oh, this current density at the given time will equal to the velocity at that given time. So you can also express like this. Right? So the amount of current, or the amount of the current being generated, depends on number of electrons per unit volume times velocity, right? So to have large current density, you need either large number of electrons per given volume or the large amount of drift velocity, right? So this was the Drude model, and I hope this was your very nice review for what you have learned previously, right? Okay. So electron motion in a solid. So in a conductor, to conduct, let me try a little thinner. All right, let's try this. Okay. So in a solid, as I said, the charge carrier is electron. Oops. All right. And here it says, a conduction electron in the electron gas moves about randomly in a metal with a mean speed u, being frequently and randomly scattered by thermal vibration of atoms. In the absence of an applied field, there is no net drift in any direction. So here, the final part is very important. In the absence of an applied field, there is no net drift in any direction, right? So even though there is no electric field, these electrons will still move around. Why? Because these individual atoms, right, it vibrates, right? It vibrates randomly, right? And this is a thermal vibration of any given atom, right? So electron moves around, but no net drift, but there is no drift velocity. If you sum up all these velocity vectors, they become zero, right? However, in the presence of an electric field EX, there is a net drift along the x direction, and this net drift along the force of the field is superimposed on the random motion of the electron. Okay. After many scattering events, the electron has been displaced by a net distance of delta x from its initial position toward the positive position. So in reality, instead of just moving this much in a straight way, it will still collide with all these atoms, right? There's atom, right? So this will move around, right? However, it will, if you add all these vectors together, you will finally get a net velocity component in x direction to the positive terminal. Okay? All right. So the velocity gained along x, right, is that the velocity gained in the x direction at the time t from the electric field EX for 3 electrons. There will be n electrons to consider in the metal, right? So for the first electron, right, all their time will be different, right? Their time is different, and from this actual drift velocity, the vector component of this individual electron, right, there will be a difference to a given time. Okay? All right? So this is what it is said. If you need more explanation, I believe this figure is explained nicely somewhere in the textbook. Okay? All right, so let's come back to this thing. So this electron motion in solid, let's say we only consider electric field. Let's only consider all right, let's just talk about this current density only generated by this electric field, right? From the previous, in a couple of slides ago, we learned that current density in x direction at a given time t equals charge of single electron times number of electrons in a given volume and the drift velocity in dx at time t. Right. In many systems, well, this value is fixed, right? The charge of single electron is fixed. The number of electrons or the number of free electrons on a given volume is constant. So this is constant. And this is generally fixed. Okay? All right. So if you think about this, go back to the high school physics again. So we know that force equals ma. Right? And then from here we can get A equals F over M. Yeah, let me just get this to... All right, here we go. All right. And then here, what I want to do is the force acting on an electron is Coulombic force, right? Over The mass is the mass of electron. Okay. And here we know that acceleration equals, yeah, let me change the thickness. I'm sorry, I should have done this before the lecture, but anyways, as dv over dt. And from this, we can get dv equals acceleration times dt. Okay? Okay. So the actual, velocity equals, so the velocity of the electron, given whatever number of electrons, should equal uxi. So this is v. Let me make this clear. Vxi equals uxi plus e times ex over me times t minus t. Right? So let's break down this individual terms. So this ui is velocity x direction right after collision. And this is last collision. So here what we are doing is that, so you can just simply say, oh, the v final equals v initial times acceleration times delta t. This is exactly what this equation is talking about. Okay? And here, we know that, we already know that, the drift velocity x is equal to 1 over total number of atoms times Vx1 plus Vx2 plus plus Vxn. Right? And in this case, average the net ui equals 0. So as I have said, right after collision, all electrons will bounce off this vibrating atom, and they will have a certain amount of velocity along x direction. But if you add all velocities of these all electrons, then the net uxi is 0. Okay? So if you consider all these, what this means is that you can take this part away. So if I write down this, so by using these two things, if I again write down, then what I get is the drift velocity in x, or the velocity of electron in x direction due to the Coulombic force, is equal to E over EX over ME bar T minus TI. And of course, this bar, it means average, and this term is average free time or mean scattering time, and symbol is tau. So basically this is the average time of electron that electron can travel without any collision. Okay? 그러니까 전자가 자유롭게 움직일 때, 그죠? 그 시간 곱하기 일반적인 평균적인 가속도, 일렉트릭 필드로 인해 생기는 가속도를 곱해주면, 예, 우리가 전자의 x 방향에 대한 드리프트 벨로시티를 구할 수 있습니다. Right? Okay. So if this is a bit hard to follow, please pause the lecture here and write down this by yourself and try to digest as much as you can. Okay, so if you simplify this, then what you get is E times tau over ME times EX. And this is the velocity of electron along x direction due to the applied electric field. Right. And there is a fancy word giving this, right? So the regularly, this free time, average free time, or mean scattering time, the scattering time of electron, right, depends on how closely the atoms are packed, or how far away these atoms are, right? So this term here in a fancy word can be said as mu d, which is E times tau over ME, and people call this as drift mobility, or the famous electron mobility, with the unit of centimeter squared over voltage times second. All right. Okay. So the one thing I want to mention is here that, okay, let me change the color of this to, yeah, let me try this one. Okay. 좀 복잡한데 계속 따라오셔야 됩니다. This one is closely related to the scattering of electrons in metal. Okay. So, for example, there can be, due to the lattice vibration, right, or crystal imperfection, right, or impurities, right, right. Okay. So the one thing I want to point out here is that this free time becomes shorter if there is large lattice vibration, or there is large number of imperfection, defects, impurities, right? Then this tau becomes smaller due to all these factors, right? So that is why we want a pure metal without any impurities or defects to achieve very high conductivity. Okay? Okay, so now let's get into our more familiar topic, right? So, as I said, this scattering time, or mean average free time, is very important. Okay? And if we consider that this is velocity of an electron or any particle, right? The relaxation time, the scattering time tau can be expressed as L over or divided by this velocity. And this distance that it travels without any collision is called the famous mean free path. Okay, this is very important, so I'm going to write another line. Mean free path. And this is an average distance between collision for a particle. An example, a charge carrier or electron. Okay, so as I said, if an electron can travel without any collision, the distance from right after the collision up to the position right before the collision, that is called the mean free path, right? So if you think about a particle, so this is individual particle here, very beautiful circle, right? If they make a slight contact, then we can say this is collision. 그죠? collision, 뭐 자동차 충돌, 그죠? 자동차끼리 뭐 우리가 키스 났다라고 하는데 입술과 입술이 맞닿는 건 쪽 그렇게 닿는 것 같은 그렇게 차들끼리 닿도, 그죠? 뒷목 잡고 내려서 보험 부르고 난리가 나죠, 그죠? Right? So that is exactly the collision, right? So even though these particles barely touches each other or make a very small contact, we still call them a collision. So the effective collision area is pi d squared, right? Or basically R. So this is 2R or 4R or equal to 2D, right? So that is this total area. Okay? And let's look at here. If this is the average velocity of an electron, right? V bar is the average velocity of electron times t, then this is the total distance. In x direction over time t, right? And this is the effective collision area, right? Then this is total is the volume that the single atom can occupy while it travels. Okay? Okay, so this thing can travel in a v direction, and it'll occupy this much volume while it moves, right? It'll go through this amount of volume when a particle moves in a given time t. Okay? Okay, so if you do this in a more fancy way, I'll just wrote down this in the lecture note already. The mean free path could be taken as the length of the path divided by the number of collisions. Okay, so if we know, let's say we define a length of the path. Let's say we just define some arbitrary length of path. And divide that length, let's say this is a large L, and divide it by the number of collision. Right? Then this will become mean free path. Okay? So we can estimate using this approach. So this is the mean free path estimate. Okay, the total distance traveled by an electron or the charge carrier or of any given particle is the bar velocity, the mean velocity times time, right? Again, this is time, right? Over the volume of interaction, this volume right here, this one right here, right? This volume times number of molecules per unit volume. Okay? Okay? All right. So if we know how much volume is required for a single electron to travel without any collision, and then if we know the number of molecules per unit volume, right? Then we know how many collisions will happen, or how many times this volume will be overlapped. So we can estimate the total number of collisions. So, right? So if we know the volume that single molecule would occupy without any collision, and if we know the number of molecules per unit volume, right, then we can logically guess or predict the number of total collisions. So if you divide this total distance by these two values, the mean distance per collision, or the mean free path, will become this, right? And this is diameter of molecule. Right. So the one thing we can find out here is that, if the molecule is smaller, then the mean free path will be larger. If the diameter is large, the mean free path will be shorter, right? So if an ant, 개미가 걸어다니고 있어요, right? In this, let's say the ant walks around the campus. The chance of ant colliding to another ant is very small, right? But if the elephant, right? Elephant walks around this campus or this classroom, then the chance of elephant encounter another elephant is much higher than that of ant, right? And another is that the NV, the number of molecules per unit volume, right? This is also important. And this is generally determined by temperature and pressure by the definition of thermodynamics. Okay? However, the problem with this expression is that the average molecular velocity is used. But the target molecules are also moving, right? So here, the molecules make collision with another molecule. If one molecule is fixed and only one molecule is moving, then the assumption of using this average molecular velocity is correct, is valid. However, both molecules are moving around at this velocity, right? So we cannot really accurately predict the number of collisions using this above equation here. So what we have to do is that the frequency of collisions depend upon the average relative velocity. 그죠? 상대 속도 of the randomly moving molecules. So there are these randomly moving molecules, and they need to find their relative velocity. Okay, so we need to account for the relative velocity, and here again, I just gave you all these thing that right. So let's say these two molecules have random velocities of v1 and v2, right? There are two vectors with different directions, right? If, however, when this molecule looks at this v2, the relative velocity is different, right? The relative velocity will be different from the actual absolute velocity. And we can calculate this relative velocity by subtracting another velocity from the original velocity, right? So the relative velocity seeing from 1 to 2 is this one right here. Okay? All right? So this is the vector of relative velocity. And the actual, all right, this value, scalar value, is the dot product of these two over root. Okay? So this velocity, relative velocity, is a form of vector, right? So you take dot product, and if you take square root, then this is your relative velocity, right? Okay? And if you do some simple math, this is what you get. Okay? And when you take dot product, if, right here, it is very straightforward, right? The dot product of the same v1 and v2, right, is simply squared, okay? The dot product between v1 and v2 two vector is simply 0 because they are not correlated. Okay? All right. So it simplifies into this form, and if you do a further simplification, the average relative velocity is root 2 times the average velocity of a molecule. Okay? So using this approach, the effective volume of target swept, instead of using just the velocity, we need to use this relative velocity, right? Okay. Okay. So if molecules moving around, right, there is possibility of collision, which is more than the stationary targets by root 2. Okay, the chance of collision increases by root 2. Okay. All right. So this lambda is a famous expression for mean free path. Right, and this equals 1 over root 2 times pi d squared times number of molecules per unit volume. Okay. Okay. And if you do this in more fancy way, this number of molecules per unit volume is n times Avogadro's number, right? Okay. And this is the famous gas constant. Or the number of moles, right? And so this here, right? And then you apply this idle gas law that you have learned in thermodynamics, right? PV in nRT, right? PV equals nRT, and N is number of moles. Universal gas constant. Oh, sorry. Yeah, this is, I'm sorry. What am I doing? Yeah, this is number of moles. Okay? And this is temperature in Kelvin. So if you do a further reduction, what you get is this one right here. I just wanted to get to this part. So the mean free path equals R, the universal gas constant, times temperature over √2 times pi times molecular diameter squared times Avogadro's number times pressure. Okay? All right. Okay. So if you break down this equation right here, here, this lambda is mean free path. R is universal gas constant. So this is constant. Avogadro's number is constant. Okay. √2 and pi is constant, right? So the three factors that determines the mean free path is T, temperature, P, pressure, and D, right? Okay, so these are the three factors. Okay? All right. So let's look at this example here. Given that the mean radius of an air molecule, either O2 or N2, which consists more than 90% of air, is about 0.15 nanometer. So we know R here. So this is radius. So diameter is 0.3 nanometer. What is the approximate mean free path of molecules in an air at atmospheric pressure and room temperature? So atmospheric pressure, 대기압, right, which is 1.1.3 kilopascal or 1 bar or 720 torr, right? Or at room temperature, so this is about 300 Kelvin or 293 Kelvin, whatever, right? Okay, so if you do all these calculations, what you finally get is that mean free path of air in ambient condition is about 400 nanometer, right? So this is very short. So every air molecule is colliding in every 400 nanometers. Okay? All right. So here is a relation between the mean free path and pressure. Okay? As we said, the mean free path is proportional to the T. Mean free path is inversely proportional to the D squared. And mean free path is inversely proportional to pressure. Okay, so this is log plot, right? So if the pressure goes up, then the mean free can also increases. And this, as you can see, it can go up to tens of feet. So if you can achieve very high vacuum, then the distance of a molecule that can travel without any collision becomes much, much longer, right? That is why the electrical conductivity, right, goes up in high vacuum. Or when you do metal deposition in microfab, or whether you are using a sputter or evaporator, right? So I believe some of you are using evaporator, or some of you are using sputter, right? And the common thing about these two tools is that they require high vacuum. And this is because this metal or the deposition material molecules have to travel long enough to make an encounter with your target substrate or a wafer. Okay? Okay? Oh, it's exactly right here, right? Right? Okay? Good. So if you go into a little more topic, there's an effect called nanoscale confinement. Okay, so this is nanoscale, right? So this is like this. When the physical dimension of a structure becomes comparable to lambda, then this physical structure itself affects the movement of a particle. It's a bit long definition, but what I want to say here is that when the physical dimension of a structure becomes comparable to lambda, right? So if a material becomes small enough that a particle collides with its edge or its physical structure itself before making a collision with another molecule, 그죠? 그러니까 몰레큘 대 몰레큘로 충돌이 일어나는 게 아니라 몰레큘이 이러한 스트럭처가 너무 작아지면 스트럭처 자체와 이렇게 부딪힐 수가 있겠죠, right? So if this boundary separation, right, or this wall separation is lambda b, right, the effective mean free path is this 1 over boundary separation plus 1 over mean free path and free space. Okay, so here what I want to emphasize is that the smaller physical dimensions governs the collision time. So if the dimension becomes small enough and it becomes somewhat similar or slightly larger than the original mean free path, then it starts to interact with the movement of an atom. Okay, so it governs the collision time. So this is the nanowire width. I'm not sure if this is silicon or gold, but this is the nanowire width, right? And here, this is the conductance over bulk. Right, so the lower volume means that the nanowire conductance is much smaller than that of bulk. And here you can see that it decreases sharply as the dimension becomes smaller. Okay? And this is, well, this is doping level. Right? Well, I'm going to talk about this doping in silicon part. So if you are not familiar with doping or the extrinsic charge carrier, you can just disregard this part. Okay? All right, so I'm not sure if this exactly is 75%, but generally I go really fast and when I record this lecture. So so I'll talk about this temperature part in next week, but what this will be what I have prepared for today. Okay? Well, again, sorry for this recorded lecture, but hope you guys enjoyed this video. And also, I hope you guys have a very productive weekend. Be safe, have fun, enjoy the weather, but please keep the social distance. Okay? All right, thank you guys, and I'll see you next week. All right, bye bye.